Directional derivatives and the gradient vector. The directional derivative finds the rate of change of a function of two or more variables in any direction. So we're not just finding the slope of the tangent line, we're taking it in the direction of a certain vector. So let's look at, first of all, how is this helpful? So if we were to look at this map, it's a contour map. It's a weather map, and it shows the level curves or the isothermals and the temperature. So here we're looking at Reno, and we could look at the partial derivative t sub t of x, the partial derivative with respect to x. Now, this would be the rate of the change of the temperature with respect to the distance as we travel east from Reno, and t of y would be if we travel north. Well, it would be negative if we're going south, and t of x would be negative if we're going west. So if we're traveling southeast, then that's where your directional derivative comes into play. It allows you to not just travel directly east and west or directly north and south. It lets us look at other directions. Therefore, it's called a directional derivative. So if you look at box 2, the definition, the directional derivative of f at that point in the direction of your unit vector AB. So notice it's a unit vector because that's an important statement here. Then that is your definition of a derivative if the limit exists. So let's take and make this a little bit nicer notation, a little bit easier to use. So in box 3, the theorem says if f is a differentiable function of x and y. So that's the big part there. And f has a directional derivative in the direction of any unit vector u equal to the vector AB. Then this is our notation here, this d sub u. This is your directional derivative notation. It happens in both of these. So the directional derivative of f at xy is equal to the partial derivative of x at xy times a plus the partial derivative of y with respect to y of xy times b. So we're going to use this. I'm going to go ahead and give you the other formula so that we don't have to list our formulas like 12,000 times. So let's say d sub u, make sure it's a sub u and not a du, f of xy is equal to your partial derivative with respect to x of xy. And instead of a, we're going to use cosine of theta, which probably makes sense because that means we're in the direction of x, plus your partial derivative with respect to y of xy, and this is going to be sine of theta. So those are the two formulas you need for the directional derivatives. If I were breaking this section up into pieces, there are 7 pieces to it. Your directional derivative happens a couple times, and there's really only like 3 or 4, but this would be Roman numeral 1, the directional derivatives. So these are the two formulas we need, both of these here. So these are our formulas for our directional derivatives. Now let's look at how this comes into play. This is just kind of a pictorial. It's the picture used to do the proof, so you can see the tangent line on that plane, the tangent line to the curve of the surface on that plane. It's just kind of a cool picture, and all of it fits together. Your book does a very good job of the proof of the definition of the directional derivative, and just kind of wanted you to see that when you look at the tangent line, it is a plane that cuts through the figure. Use the weather map below to estimate the value of the directional derivative of the temperature function at Reno in the southeasterly direction. So southeasterly is the red line that you see here. So if we were going directly east or west, we could use, if we were going directly east, we could do our partial with respect to x, and directly north, our partial with respect to y. But because we're traveling in a different direction, we have to use a directional derivative. So what we're going to do is we're going to think of it as your directional derivative as your slope of your tangent line. And that's really what we're doing here. So look at the fact that they drew the line for us southeasterly. So it's going south and east. And remember that it's never eat shredded wheat. I don't know if you've ever heard that, but as you travel clockwise, never eat shredded wheat. So if you start in the center, southeast is this way. So as you can see, our line goes that way, and it's going to start at Reno and continue on. Now, starting at Reno is not helpful, but if we go just above that, we have a temperature of 50 degrees. So we have a temperature of 50 just above Reno, and we have a temperature of 60 just below Reno. And we need to pay attention to the fact that these are our y values. These are our temperature values. So these are our y values. And then we need to estimate this distance from here to here. So we're going to pick up the distance down in the bottom using the key. And I'm measuring with my pencil. It's not the best way to do it, but I'm going to go with this is about 100. So I'm gonna cheat and say the book says it's about 75 miles. So it's approximately 75 miles. So when we look at this, we say that the directional derivative then is the slope of the tangent line. So it's going to be the y values, 60 minus 50, over the change in x is about 75 miles. So we have 10 degrees per 75 miles. So that means we have approximately 0.13 degrees Fahrenheit per mile. So that's how the directional derivative comes into play. Estimation's not fun for us. We've never found it fun, but it's useful, and this is what they use to determine the change in temperature. So here we're supposed to find the directional derivative given this equation and a unit vector. We need net vector notation, given by the angle pi over 6 measured from the positive x-axis. By the way, that formula I gave you earlier is always when you're measuring from the positive x-axis. That's your pole, that's your origin, that's your starting point all the time. So keep that in mind. So let's start with our partial derivative with respect to x. It's going to be 3x squared, and then minus 3, the derivative of x is 1, and you're left with y. So now we're going to find our partial derivative with respect to y. And the first term is going to be 0. The second term is going to be negative 3x. The derivative of y is 1, plus 8y. So now our directional derivative of f is equal to the partial with respect to x at xy. And we're going to use our cosine theta, plus the partial with respect to y at xy. And we're going to say sine of theta. So let's fill this in. We're going to say the partial is equal to the derivative with respect to x is 3x squared minus 3y. And cosine of pi over 6 is square root of 3 over 2. Plus our partial with respect to y. Oh, we don't want to write that. Our partial with respect to y is negative 3x plus 8y. And sine of pi over 6 is 1/2. Now, you can factor out the 1/2 or you can just distribute. So we have 3 square root of 3 over 2 x squared minus 3 square root of 3 times y all over 2. Let's write that a little bit differently. Over 2 times y minus 3/2 x plus 8 times 1/2 is 4y. So that's our directional derivative of this function, and then we could find it at any point. So now we're going to find it at the point 1, 2. So we're going to plug in 1 for x. We have 3 square root of 3 over 2 times 1 minus 3 square root of 3 times 2 over 2 gives us 3 square root of 3. Minus 3/2 times 1 is 3/2. Plus 4 times 2 is 8. So we have some crazy things going on. Let's get the common denominator of 2. So if we put all of this over 2, we have 3 square root of 3 minus 6 square root of 3 minus 3 plus 16. So negative 3 plus 16 is 13, and we have minus 3 square root of 3 all over 2. That is our directional derivative of that function at the point 1, 2. Now what's important here is that's a 3 square root of 3 is a little more than 5. So it's a positive value as we travel away from 1, 2 in the direction of that derivative. And this is the picture that's given here. It's a little bit prettier if you look at your book online. But here we have the directional derivative shown in the way it intersects the surface. You can kind of see it all happening there. The gradient vector is written this way. So the gradient of f, they say it's red del f. I call it the gradient of f. And it's the vector of the partial with respect to x, the partial with respect to y. Now, that's important because if you look at the directional derivative, it says the partial with respect to x at xy times a plus the partial with respect to y of xy at times b. So we could call this the partial with respect to x times the partial with respect to y times the vector ab, or we can call it the partial with respect to x, the partial with respect to y times u. So this notation here is helpful because we're going to use this vector, the partial with respect to x, the partial with respect to y. This vector right here is used a lot. So we're going to go ahead and give it a name and call it the gradient of f, and we can say with the dot product of u gives us the directional derivatives. So the gradient is that important vector that we're going to use a lot. Why we didn't name it first, I don't know, but now that we know how to use it, this notation here is the gradient vector, and it's the partial with respect to x, the partial with respect to y. It could also be in multiple variables, and I know this doesn't come up yet, but we could say that we have this notation. We also can say that the directional derivative in 3 variables is equal to your partial with respect to f at xyz dot u. So it can be used in multiple variables as well, and we're going to use it in lots of ways. So here you can see the book definition. If f is the function of 2 variables, x and y, then the gradient is the vector function, gradient of f, defined as, here we talked about it, the vector, where the first component is your partial with respect to x, the second component is your partial with respect to y. It can also be written using partial derivatives and ij notation. And then down here you can see it in terms of 3 variables, and it's your 3 partials, and it's your 3 partials with ijk notation. It's a nice notation. It's your gradient of the function f. So then we can say that our directional derivative is the gradient times the unit vector u. Remember that it is a unit vector, that's why we put a u there. So given the function sine x plus e to the xy, we're supposed to find the gradient of f and the gradient of f at 0, 1. So let's start with our partial derivative. Let's say the partial derivative with respect to x. The derivative of sine x is cosine x, and the derivative of e to the xy is e to the xy, and the derivative of xy with respect to x is just y. And then the partial with respect to y, the derivative of sine x is 0, and the derivative of e to the xy is e to the xy, and the derivative of xy with respect to y is x. So now we can say that the gradient of f is equal to the vector cosine x plus y e to the xy, and the second component is x e to the xy. Now we're supposed to find this at the point 0, 1. So we're going to plug in these x and y values. So we're going to say cosine of 0 is 1, plus y is 1, e to the 0 is 1, so that just makes 1. And then we have x, which is 0 times anything gives us 0. So this answer for the vector is 2, 0. So it's not too bad. Your gradient is the vector of the partial derivatives. It's pretty nice, actually. So to find the directional derivative of this function at the point 2, negative 1 in the direction of the vector, first of all, we need to note that the directional derivative of f is equal to the gradient of f dot product vector u. Well, we're given a vector v, which is not a unit vector. So let's start off with the vector u is equal to the vector v over the length of v. So the vector v is 2, 5, and the length of v is the square root of 4 plus 25, which is the square root of 29. So we have 2 over the square root of 29 and 5 over the square root of 29. So that's our unit vector. Let me pull this in just a little bit. There we go. And we need our gradient. So in our gradient, remember that we need our derivative with respect to x. So let's start there. When we take the derivative with respect to x, we get 2x, and the y to the third is a constant, minus 0, because there's no x there. And our partial derivative with respect to y is going to be 3y squared times x squared. So 3x squared y squared minus 4. So our gradient is equal to the vector 2xy to the third, and the second component is 3x squared y squared minus 4. So now we can find the gradient of f at 2, negative 1. So when we plug this in, we get 2 times 2 is 4 times negative 1 makes negative 4. And then 3 times 4 is 12 times 1 is still 12, minus 4 is 8. So that's our gradient at that point. So our directional derivative of f at that same point is the gradient at that point, and times using the dot product, 2 over the square root of 29, 5 over the square root of 29. It's always important that you specify which product you're using. Now I'm going to check up here. It says find the directional derivative. So I'm going to go ahead and scroll up. So then we have this notation, the directional derivative of f at the point 2, negative 1. When we multiply these, we get negative 4 times 2 is negative 8 over the square root of 29, plus 8 times 5 is 40 over the square root of 29. So we get positive 32 over the square root of 29. Now that's our directional derivative at 2, negative 1. What that means is the derivative is 32 over the square root of 29. It's positive, it's increasing, and it's headed in the same direction as the vector v, which is 2, 5. Now this one is a function in 3 variables, and we already talked about that, so we're going to jump right in. And we have find the directional derivative. We're given the function to be x sine yz. We're supposed to find the gradient of f in the directional derivative of f at that point in the direction of this vector v. Again, our vector v is not a unit vector, and in order to find a directional derivative, you need a unit vector. So let's start off with finding the unit vector of v. So let's say that u is equal to v, which is 1 to negative 1 over the square root of 1 plus 4 plus 1. So we have 1 to negative 1 over the square root of 6. So let's rewrite it to be 1 over the square root of 6, 2 over the square root of 6, and negative 1 over the square root of 6. We don't rationalize denominators anymore. You're going to keep going with it, so we just kind of keep it and leave it. It's good. Now let's find our partial derivative. So the partial with respect to x is, we take the derivative of x to be 1, so we just have sine yz. Our partial with respect to y, we're going to keep the x because it's a constant. And the derivative of, I'm going to leave a little space because the derivative of sine is cosine of yz. And the derivative of yz is z when you're looking with respect to y. And then your partial with respect to z, we're going to keep the x. The derivative of sine is cosine of yz. The derivative of yz with respect to z is y. So that means that we can say that our gradient is equal to the partial of with respect to x, the partial with respect to y, the partial with respect to z. So our gradient of f is equal to sine yz, xz, cosine yz. Make sure those z's look like z's and not 2's or 7's or something else. And xy, cosine yz. Now, we're supposed to find the gradient, which is right here, and find the directional derivative at 130. So if they want the general gradient, this is it. And if they want it at the point, we're going to use the point 130 here. So we have sine of y times z is 0, so sine of 0 is 0. And then we have x times z, which is 0, so the rest of it doesn't matter, 0. And then we have xy, which is 3, and cosine of 0 is 1, so we have 3. So our gradient then is 0, 0, 3, and we're asked, so that's the first one. This is our general gradient. This is our gradient at that point. And now we're supposed to find it in the direction of v, so we're going to say the directional derivative of f at 130 is equal to the dot product of 0, 0, 3 and 1 over the square root of 6, 2 over the square root of 6, negative 1 over the square root of 6. Now when you do the dot product, you get 0 plus 0 plus negative 3 over the square root of 6. So the directional derivative is negative 3 over the square root of 6. So this directional derivative is negative, and it is decreasing in the direction of v. Here's another one. Lots of times your homework is more complicated than what they give as an example. And I hate that, you hate that. So here's one that might lean that way. So f of, and the variables are r, s, and t. So we have the function is natural log of 3r plus 6s plus 9t. And we're finding the gradient and the directional derivative. So I think it's easier to start off with your unit vector. So let's find the unit vector to be the v, which is 4, 12, 6. Those are pretty numbers, over the square root of the length of v, which is not the square root, but the length, which is 4 squared, which is 16, plus 144, plus 36. So we have 4, 12, 6 over the square root of 196, and the square root of 196 is 14. So we have 4 over 14, which reduces to 2 over 7. We have 12 over 14, which reduces to 6 over 7. And we have 6 over 14, which reduces to 3 over 7. Now our partial derivative with respect to x is the natural log of this. Oh, not x, r. The partial derivative with respect to r is equal to the natural log of that, which is 1 over that mess, 3r plus 6s plus 9t, times the derivative with respect to r is 3. So we have 3 over that denominator, but each term in the denominator is divisible by 3. So let's go ahead and divide them all by, let's reduce that 3 throughout the entire fraction. So I'm going to put a 1 here, and then I have r plus 2s plus 3t. Now we're going to do our partial derivative with respect to s. Again, the derivative of natural log of something is 1 over the something, times the derivative of the something with respect to s is 6. Now all of that is divisible by 3, so if I divide 6 by 3, I get 2. And on the bottom, I divide each of them by 3, and we get r plus 2s plus 3t. And then our partial with respect to t, again, we're going to have 1 over 3r plus 6s plus 9t, and the derivative with respect to t is 9, so that means we have 3 over r plus 2s plus 3t. Now, we're finding this in the point 111, so we're going to say our gradient of f is equal to 1 over r plus 2s plus 3t, 2 over r plus 2s plus 3t, 3 over r plus 2s plus 3t. It's kind of pretty. And we're going to plug in the point 111. So we have our partial with our gradient of f at 111 is equal to, well, r plus 1 plus 2 plus 3 is 6. So we have 1 over 6. We have 2 over 6, which is 1/3. And we have 3 over 6, which is 1/2. Now we may wish we'd kept them all in terms of 6 when we do our dot product for our gradient, for our, of the gradient and the unit vector to get our directional derivative. But here it is. All right, so our directional derivative of u in terms of s, r, s, t, I'm struggling with that today. You ever have those struggles? Is equal to the gradient of f times the unit vector. So we're going to say this is 1/6, 1/3, 1/2. Let's go ahead and put those with common denominators. So 1/6, and this would be 2 over 6, and this would be 3 over 6. And our dot product with 2 over 7, 6 over 7, 3 over 7. Those will work out very nicely at this point. So 1 over 6 times 2 over 7 is 2 over 42, which reduces 1 over 21, plus 12 over 42, which reduces to 6 over 21, plus 9 over 42, which does not reduce. So that makes me sad that I reduced the other ones. That's okay. 2 plus 12 is 14, plus 9 is 23 over 42. So this is our directional derivative of the given function in the direction of the vector v. Suppose we have a function of f of 2 or 3 more variables, and we consider all the possible directional derivatives at a given point. There are a bunch of them, because these vectors can go in any directions. So the rates of change in all the possible directions are our directional derivatives. So then the question is, in which of these directions does f change the fastest, and what is the maximum rate of change? So this theorem answers that question. This is your maximum directional derivative. So it says, suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative, du, f of x, is the length of the gradient at x. And it occurs when u has the same direction as the gradient vector, gradient of f. So what's important here is the maximum then. The maximum value of the directional derivative, or the maximum directional derivative, is the length of the gradient of f. And it occurs in the same direction as u, in the same direction as u, your unit vector that you find. So we have an example. So if f of x equals e to the xy, find the rate of change of f at the point 2, 0 in the direction from p to q, where you're given those values. Now we know the rate of change is the directional derivative. So let's start off with, first of all, we need a vector and then we need a unit vector. So let's let v be equal to the vector from P to Q. Since we're ending at Q, then we're going to do 1/2 minus 2 to be negative 3/2, and 2 minus 0 is 2. So that is our vector v. And then our unit vector is v, which is negative 3/2, 2, over the length of v, which is the square root of 9 over 4. 3 squared is 9, 2 squared is 4. Just checking that. Plus 4, which is interesting. So we have negative 3/2, 2. When we add those, we get 25 over 4. So we have u to be negative 3/2, 2, and the denominator is 5/2. So that means that we have negative 3/2 over 5/2 is negative 3/5. And negative 2 over 5/2 is 4/5. Need the gradient. So let's start with our partial with respect to x. The derivative of x is 1, and we have e to the y. The derivative with respect to y is e to the y, and we keep the x. So that means our gradient is equal to e to the y, and the second component is x e to the y. So our gradient at the point 2, 0, because we're supposed to be using this point P. So our gradient at the point 2, 0 is equal to e to the 0 is 1, and 2 times 1 is 2. So that's our gradient. Now we need our directional derivative to find the rate of change. So we're going to say du f of 2, 0 is equal to the vector 1, 2, and the dot product negative 3/5, 4/5. So when we multiply these, we get negative 3/5 plus 8/5, which is 5/5, 1. So our rate of change is 1. So that's the first part of the question. And then it says, in what direction does it have a maximum rate of change? And what is the maximum rate of change? So let's go back up here. Remember that our maximum rate of change is the length of the gradient. So we have our rate of change. Now let's find the maximum rate of change. So we're going to say the length of the gradient of f is equal to, we're going to do the length at the point 2, 0, which we already found that to be the length of the vector 1, 2. So that's nice, easy math. The square root of 1 plus 1 is 1, and 2 plus 2 is 4, so we have the square root of 5. This is our maximum length of our directional derivative at the point 2, 0. Now what this says is f is increasing the fastest, and this rate of change is the square root of 5 at that point. The second part of that also says, if we go back to the question, it says, in what direction does f have the maximum rate of change? So the direction is the direction of the gradient vector 1, 2. So we can say that the direction of the gradient vector, let's say the gradient vector is this. So we have the vector 1, 2. So going back to the direction up here, it has the same direction as the gradient vector. So the maximum directional derivative is the length of the directional derivative, and it occurs in the same direction as the gradient vector. So what we found is our rate of change is 1. Our maximum rate of change is the square root of 5, and it occurs in this direction. Hopefully that makes sense. But before we switch slides, wrong thing, but before we switch slides, here you can see the pictures that they're given. So notice from figure 7 that this vector appears to be perpendicular to the level curve. Figure 8 shows the graph of f and the gradient vector, but it confirms everything we were looking at. This is a good example here. It says, suppose the temperature at a point x, y, z in space is given by this function T equals, where T is measured in degrees Celsius and x, y, z in meters. In which direction does the temperature increase the fastest at 1, 1, -2, and what's the maximum rate of increase? So we know that the direction is our gradient, and we know that the maximum rate of increase is the length of the gradient. So we're not even asked to find the directional derivative at this point. We just need the gradient and the length of the gradient because it doesn't say what's happening at that point. So let's start with, in order to find the gradient, we need t sub x. And let's not do that yet. Let's rewrite t to be 80 over 1 plus x squared plus 2y squared plus 3z squared, which can be written as 80 times 1 plus x squared plus 2y squared plus 3z squared, all to the -1. You can use the quotient rule if you'd like, but the fact that the top is just constant makes it easier to use the chain rule. So t sub x is equal to the derivative of 80 times something to the -1 is negative something to the -2. So we have 1 plus x squared plus 2y squared plus 3z squared, all to the -2, which moves it to the denominator, by the way, times the derivative with respect to x is 2x. So we're going to say that t sub x is equal to negative 80 times 2 is negative 160, and the denominator is 1 plus x squared plus 2y squared plus 3z squared, all squared. I'm going to bounce off of that and find t of y. And I know that the derivative is negative 80 times the parentheses to the -2. And then the derivative with respect to y is 4y. The derivative of 2y squared is 4y. Just double checking. So we get negative 320y over 1 plus x squared plus 2y squared plus 3z squared, all squared. And now we need to find our derivative with respect to z. So t sub z is negative 80 times 1 plus x squared plus 2y squared plus 3z squared to the -2. And the derivative with respect to z is 6z. So then we have negative 6 times 80 is 480 z. And the denominator is 1 plus x squared plus 2y squared plus 3z squared, all to the squared power. So we see a pattern here. So our gradient with respect to f, our gradient of f is equal to, I'm going to say the numerators are negative 160, negative 320y, and negative 480z, all over the same denominator. So I'm not going to write it every time. 1 plus x squared plus 2y squared plus 3z squared, quantity squared. Now I'm going to go back to splitting it in a few minutes, but we're supposed to be using the point 1, 1, -2. So let's do the gradient of f at 1, 1, negative 2 is equal to, the denominator is parentheses 1 plus 1 plus 1 squared is 1 times 2 is 2 plus 4 times 3 is 12, all squared. And the top is negative 160, negative 320, and positive 960. Now the bottom is 12 plus 2 is 14, 15, 16. Squared is 256. I think I'll keep it separate for now. So we have negative 160, negative 320, and 960 all over 256. Now these numbers are large, and if you think of them as a fraction, so we have the gradient of f at 1, 1, negative 2 is equal to negative 160 over 256. By the way, both those numbers are divisible by 16. Negative 320 over 256, again, obviously, and 960 over 256. So let's reduce all of them by 32. So the first one will be negative 5 over 8. And I'm going to keep the common denominator of 8 because of where we're headed. The next one would be negative 10 over 8. And the last one would be 30 over 8. If I were to divide the denominator by 32, divide all the top by 32. Now, if I were just supposed to stop at the gradient, I would say the gradient of f at this point, let me put it in a different color. So I'd say the gradient of f at this point is equal to negative 5 over 8, negative 10 over 8, 30 over 8. But let's reduce those because a final answer for a gradient alone would be negative 5 over 8. This would reduce to negative 5 over 4, and 30 over 8 would be 15 over 4. But we're not stopping there. We need to find the maximum. So this is the direction of the directional derivative, and then we're asked to find the maximum rate of change, which is the length of that. That's why I kept those denominators the same. We're going to say the square root of 5 over 8 squared is 25 over 64, plus 10 over 8 squared is 100 over 64, plus 900 over 64. So we get the square root of 1025 over 64. So we need to simplify that. Let's pull out a 25. So we're going to say 5 over 8, and inside we're left with 41. Yeah, I did it on the side and came back. I'll let you simplify that radical on your own. So this is our max. This is our max directional derivative, our maximum rate of change, our maximum directional derivative, and this is the direction of it right here. So these are the two parts we're looking for. Now it doesn't actually ask us to find the directional derivative. It says in which direction does it increase the fastest, and what is the maximum rate of increase? So our direction is in the direction of the vector negative 5 over 8, negative 5 over 4, 15 over 4, and the maximum rate of increase is 5 over 8 times the square root of 41. So we can call this to be approximately 4 degrees Celsius per meter. Remember that the T is in terms of Celsius and the variables are in terms of meters. So that helps us to figure that out. So now we have tangent planes to normal surfaces, and this looks like it did before. So the top one here is our tangent plane, and it's exactly what we did before. If you look at it, we have our partial, and then x minus x sub 0, our partial derivative with respect to y minus y was sub 0, and our partial derivative with respect to z, and z minus z sub 0 equals 0. And then this would be our normal line, and it looks like it did before as well. So these aren't overly difficult, and they look the same. It's just, how does that change into the gradient? Well, it's what we were doing before, and we're going to show a picture of it. But I don't know that we need to do a bunch of these because we have. So let's do one. So we're going to find the equation of the tangent plane and the normal line to the ellipsoid in green at the point also in green, a different color green if it matters. So the first thing we do is we say the ellipsoid is the level surface, and f of xyz is equal to x squared over 4 plus y squared plus z squared over 9, and k equals 3. So that's the level surface is k equals 3, but this is our function that we have here. So now we're going to find our partial derivatives. So the partial derivative with respect to x is 2x over 4, which is x over 2. I like 1/2 x. Our partial derivative with respect to y is 2y. Our partial derivative with respect to z is z squared over 9. So this will be 2/9 z. The next step in the tangent line is the tangent plane, is to find the value at the point given. So we have -2, 1, -3. So when we plug in the x value, we get half of -2 is -1. When we find the partial derivative at that point for y, we have 2 times 1 is 2. And when we find the partial derivative with respect to z at that point, we have -6 over 9, which reduces to -2 over 3. So now we're going to find our equation of our tangent plane, and that will be the partial with respect to x is -1 times x minus 1, which is -2, plus our partial with respect to y times y minus y, which is 1, plus our partial with respect to z, which is -2/3, times z minus the z value of -3 equals 0. So this is our tangent plane right here, the equation for the tangent plane, but it needs to be simplified and combined. So let's go ahead and simplify to be -x minus 2 plus 2y minus 2 minus 2/3 z minus 2 equals 0. Now we don't want to carry fractions through here, so I'm going to multiply everything by -3 or by 3. We would like our x to be positive, so let's multiply by -3. So we have 3x plus 6 minus 6y plus 6 plus 2z plus 6 equals 0. So then we have 3x minus 6y plus 2z and plus 18 equals 0. So this is our equation for our tangent plane. General form, usually there are no fractions and your x is positive. That's why I went that way. My math lab might take it in this form if you were to simplify it and say -x plus 2y minus 2z minus 6 equals 0. I'm not sure. You can play with that if you'd like. So this is our tangent plane right here. And now we need our normal. It asks for the normal line. So when we look at our normal line, we start with our symmetric equations. So we're going to say x plus 2. I would like to zoom back out. Let me do that. So maybe I'll put it over here. So we're going to say x plus 2 over, because that would be the x minus the point value over the partial derivative is equal to y minus 1 over the partial derivative of 2 is equal to z plus 3 over the partial derivative of -2/3. So you have this form, and that is the form for the symmetric equations for the normal line. And it appears that that's all you're supposed to have to type. I would change that a little bit if it was me, but I will not. So the significance of the gradient vector. First, think of a function f of 3 variables in its domain and the point at a point P. So we know that the gradient vector gives the direction of the fastest increase of f. And we also know that the gradient is orthogonal to the level S, to the level surface S of f through P. So you can see this happening here. So we know it gives the direction of fastest increase. We know it gives the length of f, gives the amount of maximum increase, and we know it's orthogonal to that point. So these two properties are compatible intuitively. Because as you move away from P on the level surface of F, so as you move away from P, that's a terrible color. Let's try again. So as you move away from P on the level surface S, the value of F doesn't change at all. So it seems reasonable that if you move in the perpendicular direction, you get maximum increase. So all of that ties these concepts together. In like manner, consider a function f of two variables and a point P in its domain. Again, the gradient vector gives the direction of fastest increase, and because of tangent planes, it can be shown that the gradient vector is perpendicular to the level curve that passes through P. Again, this happens because f remains constant as you move along the curve. So the properties of the gradient vector, consider the gradient vector f. So the first one is that your directional derivative, so number one, your directional derivative at xy is equal to the gradient times the dot product of the gradient and the unit vector u. Secondly, the gradient of f is the direction of maximum increase. And the length of the gradient is equal to the maximum increase, or the maximum rate of increase. Let's say maximum rate of increase. And then number three, we know that the gradient of f is perpendicular to the level curve or level surface through f. Is perpendicular to the level curve or level surface through of f through x. So those are all very good properties that you should pay attention to. It kind of summarizes what we've been doing. If we consider a topological graph here of a hill and let f of xy represent the height above the sea level with the coordinates xy, then this curve of steepest ascent can be drawn by making it perpendicular to all the contour lines. So you can see that they did that here. And lastly, mathematical software can plot sample gradient vectors, where each gradient vector, the gradient of f at AB, is plotted starting at the point of FB, and it's called the gradient vector field, superimposed on a contour map of F. So you can see that the gradient vectors point uphill and are perpendicular to the level curves. So that's an interesting thing to look at before we move forward. So the big things here are your directional derivative, your gradient, your rate of change, your maximum rate of increase where it occurs, and your tangent and normal planes. I hope that you understand this lesson.